Okay, let's unpack this. We talk constantly about smart cities and connected infrastructure, data flowing from traffic signals, cameras, sensors.
All the time.
But take a minute and visualize that flow. How does the simple text message you send or the complex signal timing data
Yeah.
actually transform into something that can travel across a fiber optic cable?
Right. How does it get delivered to the one precise device it needs to reach out of, billions?
Exactly.
That underlying mechanic, the very language, and the postal system of digital communication, that's what we're diving into today. We're going straight to the fundamentals.
There's like in data packets, IP addresses, all of it.
All of it. And we're basing this on some fantastic source material.
We dug into a session from the ITS Masterclass, pulling straight from the course that really forms the foundation here, titled Networking 101, Digital Communications and IP Addresses.
And we absolutely have to start with a key acknowledgement. This foundational educational deep dive was created and presented by the AtkinsRealis team for the Florida Department of Transportation, FDOT.
So our mission today is to give you a shortcut to really understanding this. We're aiming to hit three things. First, we need to master the core mechanism of digital language itself.
Second, we're going to define that crucial relationship between the Internet protocol, the IP, and the physical hosts and networks that you actually manage out in the field.
And most practically, we'll get into why IP address classification even exists. Why did engineers have to invent these size-based rules, and why did wasting addresses become such a massive problem?
It dovetails perfectly off our last discussion on fiber optics.
It does. Now that we understand the physical medium data travels on, we need to know what that fast-moving data is. How is it organized before it becomes, a pulse of light or a surge of voltage?
Okay, so here's the fundamental shift in thinking you need for networking. In the digital world, everything, every sound, every picture, every single letter is represented as a number. Just a number.
And not just any number, it's all binary-based. That means it can only be one of two things: a 0 or a 1, a switch that's on or off, a yes or a no.
Exactly. So any source output, a text from your phone, an instruction from a traffic controller, it's first converted into a long sequence of these ones and zeros. We call that a bit stream.
And that stream then gets encoded or prepared for whatever physical medium it's going to travel on.
Right. Fiber, copper, wireless radio waves. It doesn't matter. The language underneath is always that bit stream.
So the basic building block here is the bit, a single binary digit. But one bit on its own is, it's pretty useless.
It's too small to mean anything. So we group them. The standard grouping that everyone uses is the byte, which is made up of 8 of those bits.
And a byte typically represents one single character, like one keystroke on your keyboard.
Right. And to make sure that every computer everywhere understands what that sequence of 8 bits actually means, we use a global rulebook. It's called the American Standard Code for Information Interchange, or ASCII.
ASCII is basically the dictionary of the digital world. It's fascinating how rigid it is. Every single character, from a capital A to a $sign, corresponds to a unique decimal value between 0 and 255.
So when you press the letter Z's on your keyboard, the system doesn't see a Z. It instantly knows to translate that into the binary sequence that corresponds to the number 122.
And it's interesting you call it the American Standard.
Well, yeah, and that's a key point. It works perfectly for English. But if you're dealing with international communications, say languages with accents or totally unique characters like Cyrillic or Chinese, you need different standards like Unicode.
But the principle is the same. Underneath it all, it's still just a long, predictable stream of binary digits.
Exactly. Which brings us back to the math. We're all used to the decimal system, which is based on powers of 10.
Right.
But binary math, the language of computers, is based entirely on the powers of 2. 1, 2, 4, 8, 16, 32, and so on.
And this is so critical because it dictates the scale. With just one bit, you have 2 possibilities. With 2 bits, you get 4. But this power, it just scales exponentially.
That's why a byte, those 8 bits, can hold 256 unique values. It's 2 to the power of 8.
So wait a second. If the math scales that fast, and we're talking about modern computers using 64-bit addressing, which is 2 to the 64th power, a number of the quintillions, why is network management so hard? Why do we worry about capacity?
That is an excellent question. The theoretical possibilities are, you're right, they're vast, but the structure we imposed on the early internet, and specifically the fixed 32-bit limit on the original internet protocol, that's why we ran into so much trouble.
We basically created a container that was too small for the exponential growth of devices.
We did. But before we get to that container, let's quickly trace the journey of the data itself.
Okay, the transmission flow.
Right, so the source, let's say our traffic controller, sends that ASCII text. The source encoder converts it to binary. Then that binary hits the channel encoder, which prepares it for the physical channel.
And that channel is where it becomes, real, physical.
It is. If we're using low-voltage copper wire, the bit stream is literally created by turning an electrical current on, say, positive 3 volts for a 1, and then off 0 volts for a 0 in a very precise pattern.
And this is where we can loop back to fiber, which is so crucial for ITIS infrastructure now. With fiber optics, we're not using voltage.
Nope, we're using pulses of light. A pulse of light is a 1, and no light is a 0. And because light travels so much faster than electricity through copper, the time units are they're radically different.
Which allows fiber to carry an exponentially larger amount of data per second.
So now we've packaged the information. It's a burst of binary data ready to go somewhere. But now we need a map. We need an address to get it exactly where it needs to go.
And that brings us to the Internet Protocol address, the IP address. This is the unique identifier, the digital fingerprint for every single device or host on a network.
And under the original standard, what we call IPv4, this address is a 32-bit number.
32 bits gives us that theoretical maximum of just over 4.2 billion unique hosts, which, as you pointed out, in a world with trillions of connected devices feels impossibly tight.
It really is. And since nobody can read a 32-digit string of ones and zeros, we use what's called dotted decimal notation.
Right, we just chop those 32 bits into 4 groups of 8. We call them octets.
And we convert each of those octets to its decimal value. That gives you the familiar 4-part address, like 162.16.254.1.
Now, what's crucial to understand here, and this is the key takeaway, is that this single number is actually playing 2 different roles.
A dual role, exactly. It always consists of 2 parts, the network ID and the host ID.
And this split it's the genius of how large-scale routing works. The network ID identifies the network itself. Think of it like the neighborhood or the city block.
And it's only used for routing data across the massive global internet. Once the data reaches that neighborhood router or switch, the global part is done.
Then the second part, the host ID, gets read.
Right. The host ID identifies the specific device within that network, the exact traffic controller, the exact server. The local switch uses that host ID to pinpoint the final destination.
This idea of uniqueness is so important, especially for infrastructure engineers, because while public IP addresses are governed by global bodies, networks like the one for the Florida Department of Transportation are often private and closed.
Right, they're not reachable by the wider internet, which means FDOT can set its own internal IP schema.
And this is where management becomes everything, because we saw what happens when it goes wrong.
Oh, yeah. In 2016, the state of Florida effectively ran out of IP addresses. It wasn't because they physically lacked addresses. It was because the internal schema was so fragmented and inefficiently allocated that they couldn't assign a new device without creating a conflict.
I remember hearing about that. It wasn't just a technical problem. That re-IP effort was a massive multi-year, multi-million-dollar undertaking.
It was huge. It required coordination across the entire state and impacted every single connected piece of ITIS infrastructure. It's really the perfect case study for how these abstract networking ideas become very concrete, very painful operational realities.
Absolutely. And if we zoom into the roadside, the most common failure we see is probably the IP storm.
Yes. Think about devices like switches or cameras. They often come out of the box with the default static IP address. So if you're installing new equipment and you plug 2 identical unconfigured devices into the same network,
They both try to claim the same host ID.
and when 2 devices try to claim the same address on the same local network, communication doesn't just slow down, it breaks.
You get a storm.
Precisely. A chaos of conflicting identities leading to a communication failure that probably requires an immediate maintenance call. Understanding that IP schema and ensuring uniqueness it's the core skill that prevents this kind of avoidable outage.
Okay, so if the IPv4 limit is 4.2 billion and we're seeing all this waste and bad management, efficiency suddenly becomes the biggest engineering challenge.
It really does. I mean, if we just split the 32 bits exactly in half 16 for the network, 16 for the host, every network could support 65,536 hosts.
That sounds pretty generous.
It does, but imagine a local FDOT office that only needs, say, 1,000 devices. You've just wasted over 64,000 potential addresses in that single block. And that waste adds up globally really, really fast.
So the solution was to stop treating the IP address as a fixed 50-50 split.
That's right. This waste problem prompted the creation of IP address classification. The IP protocol defines 5 different classes, A, B, C, D, and E. Each one is designed to optimize that balance between the network ID and the host ID.
So it's about getting the right size for the right job.
Exactly. Let's start with Class A. This class is for massive, truly gargantuan networks. Think major corporations or government departments.
Okay.
They reserve only the first byte for the network ID, but they dedicate 3 full bytes, that's 24 bits, to the host ID.
So that means there aren't very many of them, but the ones that exist are huge.
You've got it. There are only about 126 possible Class A networks in the entire world. But if you have one, you can put more than 16 million unique hosts inside it. Think IBM, the Department of Defense, that scale.
Then you move to Class B, which seems a bit more balanced.
Class B is for medium-sized networks. It uses 2 bytes for the network and 2 bytes for the host. This allows for over 16,000 networks, each with capacity of over 65,000 hosts.
And then there's Class C, which seems to flip the whole thing on its head.
It does. Class C is for small networks. It dedicates 3 full bytes to the network ID, but only the final single byte, just 8 bits to the host ID.
Which means you can have millions of these small networks.
Over 16 million of them. But each one is severely limited to a maximum of 254 unique hosts.
And what about D and E?
We should mention them. Class D is for something called multicasting, and Class E is just reserved for experimental use and research, so you won't really see those in the field.
So the intention here with A, B, and C was good, tailor the address block to the organization to limit waste. But in practice, how well did it actually work?
It created what we call the Goldilocks problem. A Class B network was often still way too large, leading to waste.
And a Class C was frequently too small, forcing growing organizations to jump through hoops when they needed just one more device than the 254 limit.
Precisely. The fixed nature, defined rigidly by those first few bits of the address, became its own limitation. It wasn't flexible enough.
It sounds like what we really needed was a way to borrow bits, to customize the split based on our exact need, not just these 3 fixed categories.
That flexible customization is exactly the solution engineers came up with. It's called subnetting, and it's what gives network managers the granular control they need.
Okay, that was an essential deep dive into the fundamental language of digital infrastructure. Let's recap. Digital communication is a language universally based on binary numbers, encoded through standards like ASCII.
And that data is packaged and routed using the dual structure of the IP address, the network ID for the big picture internet routing, and the host ID for pinpointing the exact device on your local network.
And for you, the engineer working on ITIS systems, understanding this IP schema is not abstract theory at all.
Not at all. It is the absolute difference between success and failure when you're configuring roadside devices. It's vital for designing smart signal systems, for preventing those network storms from conflicting static IPs, and for ensuring that those roadside units can talk seamlessly with the RTMC.
Knowing this architecture is just essential for long-term stability and, frankly, for cost avoidance, especially when you think about the massive effort it took to fix the poor IP organization back in 2016.
And just a reminder on the curriculum, our next session, Networking 102, is going to focus entirely on the OSI model and the concept of subnetting, which is the key to solving that address waste problem we just talked about.
After that, we'll hit topology, Ethernet, and a practical application review. And this educational deep dive was proudly produced by AtkinsRealis for the Florida Department of Transportation.
Before we go, let me leave you with this provocative thought. We spent a lot of time on how the powers of 2 define network scale. Now, consider how that exact same mathematical principle, the power of 2 applied to unique combinations, is the fundamental tool used in fields that seem totally removed from computing.
Oh, that's interesting.
Think about molecular biology and genetic sequencing, where millions of unique combinations of nucleotides have to be identified, or how large-scale inventory planning uses this to manage warehouse stock. The binary foundation governs far more than just the flow of data packets across the highway.